So in general, how are you finding the content?
Okay, but
Good, sir.
some issue with the linked list.
Okay, we'll discuss that. Linked list. So otherwise, what things going for all of you in this term? So how many can someone tell me the combination of courses that you have taken along with PDSA? What all have you taken?
Sir, I've taken BDM and PDSA, 2 things.
Okay, BDM, PDSA, and others.
Sir,
I have
system commands.
So I have taken DBMS and PDSA.
Okay.
I have taken DBMS, PDS, and business analytics.
Okay. Okay.
I have PDSA, DBMS, and system commands.
Sir, I have MLF and system commands along with PDSA.
Okay.
Update to PDSA and system commands.
Okay. Dev 2, huh? So Abdev 1 you already completed that.
Yes, sir.
Nice. Okay. Right. So what we'll do today is
Sir, before you start, like I have 2 queries regarding week 2.
Okay.
Yeah. So one is like the practice assignment question 5, week 2.
Okay.
Uh,
What is it about?
So there is code given and the complexity is asked and 4 options are given. So
Okay. One second. What we'll do is I'll just note down a few things and then we can. So we'll just start. Okay. So let us not spend any more time. So I will try to note down questions and try to address as many. So you want to look at week 2 practice assignment question number
5.
Question 5.
And one more question, like in week 2 graded assignment question 8.
Question
8.
Okay. Graded assignment question 8. Okay. So others, is there anyone who's not talking? Kindly mute.
Week 2 GRPA 2.
One second. Okay, week 2.
GRPA 2.
Okay.
These things are means I have solved the problem in another way. Means not the solution provided, but I am not passing all the cases. I don't know why.
All right. Okay.
I'm facing the same issue.
This is what that this is find largest. That's the one, right?
The rotation, the least it's sorted
rotation.
and rotator. So
Okay.
I find it in a means solving in a different way, but I am failing one test case.
Okay. So these are all 3 week 2 questions. So others, are there any other questions for week 3? So we just note it down and then maybe depending on the time availability, we'll visit
So week
one.
3 the linked list, sir.
Okay, week 3 linked list. Okay. Right. Others, any other
So
issues?
same doubt with linked list.
Okay, linked list we'll discuss. So anyone else, anything else in week 3 that?
So week 3, the difference between list and array, I assume that array was a part of list. Like I understand it as in matrix. When we create matrix, it's an array wherein rows are in terms of list. So basic structure problem, difference problem I have.
Okay, week 3 list versus array. See, I thought of replit, but then probably collab is better since Professor Madhavan uses collab. So let us use.
So I have a doubt in week 2, PPA 2.
Okay, week 2 PPA 2. Okay. All right. So once again, we will call it live session. This open session, right? Open session underscore week3 dot IPython notebook. Okay. So this is week 2 PPA2 GRPA2. These are all week 2, week 3. Anyone else?
Sir, week 3 open hashing.
Week 3 open hashing.
Hello. Can an example be given in the case of linked list as in the implementation? Well, I've understood the concept. The implementation of it has not been clear, as in like how I would build one and perform operations on it.
बिल्कुल you should be. अबे call चल रही.
Excuse me, kindly muting all. So see, this we will certainly do. These I am not sure about open hashing, but not because I don't want to discuss it, but maybe tomorrow Atul might be a better person to discuss open hashing. So these two we'll certainly do, and these week 2 questions also we'll take it up, complexity based stuff. GRPA2 week 2. This week 2 deadline is over, right?
Yes.
Yes, sir.
Then there's no issue discussing. All right. So
and just one small, if you can briefly touch upon a randomized pivot in a Quicksort. Just maybe an implementation or just giving a brief idea about it. I can understand a fixed pivot, just a randomized pivot.
Okay. So randomized pivot. So week 3 we'll certainly do these things. And week 2 we have. Anyone else? Just one more minute we'll take an week 2 grade assignment 2 fine. Yeah. Anything from week 3 that anyone has? Okay. I assume that there are no more queries. So what we'll do is I will come to these questions. There are certain number of slides that I have prepared. So we will quickly run over them.
So I have one more doubt. Week 2 graded assignment question number 2. Yeah.
Which assignment, theory or
graded assignment? Question number 2.
Okay, week 2 graded assignment.
Question 2.
Okay. Okay. So
thank you.
Yeah. Seems like you all have. I think many of you wouldn't have watched the week 3 videos, right? Is that right? Or
half completed.
Yes. Okay. All right. So these are questions. We'll get back to this. Now what I will do is I'll quickly run through the slides where there is some presentation of certain things that I would like to show, and then we'll go to these questions one by one. So linked list will get sorted while we discuss this. Randomized pivot also hopefully will get sorted while we discuss this. Okay, so all right. So this is perhaps not exactly relevant to the technical content, but certain things that I want you all to note is this, right? So merge sort that we saw in the last week was actually invented by this mathematician, physicist, computer scientist named von Neumann, right? So von Neumann was a pretty great figure in sciences in general, right? Sciences and engineering in the 20th century, right? So what is interesting to note is that merge sort was introduced or invented in the year 1945, right? That's an important point to note, right? So what we see in merge sort is that it's intrinsically recursive. This is something that the professor mentions. Problems with merge sort is that it doesn't sort in place, so it creates a new array, right? So every time to store the merged elements from the two halves, right? And the heart of the algorithm is the merge operation. So we'll see why all this is important, why I'm saying all this. Next, we come to Quicksort, which is the focus of the first half of week 3. Right, so Quicksort was invented in the year 1959. So Tony Hoare, as you see, Professor Madhavan also mentions, Tony Anthony Hoare is the inventor of Quicksort, a British computer scientist. right? He discovered this particular algorithm in the year 1959 while he was a student at Moscow University, right? So this is very interesting because Quicksort that we are studying today was actually invented by someone who was actually a student at that point of time, right? And that's important to note, interesting to note. It's also, in some sense, O of n log n, and it uses the same divide and conquer strategy, which we'll be studying in greater detail in later weeks, right? But what is interesting is that Sir Tony Hoare is about 87 years old now, right? So why does this matter? This matters because the subject that we are studying, unlike the mathematics subjects that we looked at in the foundational level, is pretty recent, right? So if you look at the algorithms, if you list down the algorithms that we have that we'll be studying in this course, almost every single one of them were invented in the period 1950 to 1970, right? So you're actually looking at a 20-year period in the last century where all these algorithms were invented, and some of the inventors are still alive, right? So that shows how recent, how young the subject is, right? So this is some historical context that I would like all of you to have. It makes the study of the subject all that more interesting. Okay, so getting back, Quicksort is in place, right? This is very important. There's an important difference between merge sort and Quicksort, which is that you don't essentially need an extra array or a list to sort the elements. You can do it in place. And also, it's the most widely used sorting algorithm, Quicksort. It's an absolutely wonderful algorithm. The heart of this method is the partition operation. Okay, so please stop me at some point of time if you have any questions or if you want to follow up on a particular slide. Otherwise, I don't know if you're listening or not, right? So if something is not clear, please stop me. So Professor Madhavan in his lectures discusses one partitioning scheme, and it's called Lomuto partitioning scheme, right? So if you remember, the main idea in Quicksort is that you divide the list into two halves, right? And recursively sort each of these halves, and this whole process is called partitioning, right? So let's quickly go over a visualization of what this partitioning scheme is all about, right? So the first one is called Lomuto partitioning, which is typically discussed in all textbooks in computer science, introductory algorithms textbooks. This is the partitioning method that they use. Okay, so this is how we go about it, right? So this is something that will help you remember this partitioning scheme later on also. So you start with two indices or two pointers, right? One is called the left pointer, another is called the right pointer. What we mean by this is that this is the convention that we'll follow. Everything between left and right, is greater than the pivot, right? So the pivot, mind you, is the value, the first element in the list. Okay, in a non-randomized or very plain vanilla version of Quicksort, first element is the pivot, and you start with two pointers. Everything, the hope is that everything between these two is greater than the pivot, and everything to the left of this particular left pointer is less than or equal to the pivot, right? So is this clear to everyone what we really want to achieve?
Yes, sir.
Okay.
By default only we are choosing the first element to be the pivot element, right, sir?
Yeah, this is a default choice. So by default, we choose the leftmost element to be the pivot. So actually, if you look at textbook versions, this whatever we call the Lomuto partitioning scheme uses the rightmost element as the pivot. But in fact, if you choose the leftmost, it's slightly easier to write the code maybe. So what we follow in this course is that the leftmost element by default is the pivot.
Okay.
Okay, so now what we do is, in every iteration of this partitioning algorithm, this right pointer is going to keep moving to the right. Okay, so I look at this element here and I ask this question: is the element greater than the pivot? Right? Is 9 greater than 5? If yes, then I just I keep moving my pointer to the right. So at this stage, I again ask this question, is 8 greater than 5? Yes, it is. So I move it to the right. So now notice that everything between these two pointers is greater than the pivot, right? Anything between these two pointers, 9 and 8, greater than the pivot 5. And everything to the left of this particular pointer is less than the pivot, and that less than or equal to the pivot, right? So it's maintained. So for those of you who have understood Quicksort, the partitioning scheme, can you tell me what happens at this iteration?
3 and 9
Sir,
get swapped.
now it goes to
On
the left.
comparison 5, it is swapped with 9.
Okay, right. So what happens is 3 is less than the pivot 5. So as you mentioned, what we'll do is we'll move the left pointer to the right and we'll swap 3 and 9. Okay, so we do a swap. So it becomes 3, 9 goes there. So now this this condition is still maintained, right? So anything between the two pointers is greater than the pivot, and everything to the left of this is less than or equal to the pivot, right? I hope everyone got this. Those who have not watched the lectures also, please let me know, because this will help you watch the lectures in case you haven't.
Sir, but
how come less than equal to pivot is maintained now after swapping?
Sir, you have moved 3 before 5, no? So how is it that left to this is everything is less than the pivot? Because 5 is greater than 3, no, in this case?
No, 5 is the pivot, right? So everything to the left of 3 and left of this pointer is less than or equal to the pivot. So 3 is less than or equal to the pivot. Pivot is 5. Right? Remember that pivot is always the leftmost element in our scheme. So I'll just go forward. I'll tell you what we want. What we want is this kind of a final result where 5 is here and everything to the left of 5 is less than or equal to it. Everything to the right of 5 is greater than it. This is our final result that we want. Okay, I hope.
Okay, sir.
Yeah, so now we going back. Yeah, so now we swap, and at this stage, everything from here to the left is less than or equal to the pivot, right? So now what we do next is we move on. So the element 9 is now greater than the pivot, so there is no
Pivot is at a fixed place.
Yeah, pivot is this L of 0, right? It's the leftmost index. Okay, and our intention is to partition. Partition meaning we divide the array into two parts such that everything to the left of one part is less than the pivot. Other part to its right is greater than the pivot. This is our intention. Okay. All right. So now 9 is greater than pivot. Pivot is, remember, 5. So you move the right pointer one more step to the right. Now what we see is that this is less than the pivot. So I want this to be somewhere here. Okay. So I move this green pointer to the right, swap 8 and 2. Okay. And now whatever I want is achieved, right? Everything between is greater than pivot. Less than this is less than or equal to the pivot.
Want 2 be swapped with 3?
Yeah.
No, right? See, 2, no. Yeah, so I'll just go back to the previous time we swap. So 3 is greater than, 3 is less than 5, right? So what I do is, note that everything starting from the green pointer to its left is already in place. So what I do is I move green pointer to the right and then swap 3 and 9.
Okay, this process continues for the other elements.
Yeah. So for example, here, since this is already in place, I move the green pointer to the right, swap, right? And now I can just continue. So at this stage, in some sense, the partition is complete except for one point. The pivot is not in the right place. Okay, so the pivot is not in the right place. So what we do is we exchange the pivot with the current element that this green pointer is pointing to. So you have to swap 2 and 5. You do that. And now we have the partition.
Sir, can you just repeat this step once?
Okay, so Till this you understood, right? So this right pointer is moving to the right.
Yes, sir.
Now what happens is everything to the left of the green pointer, okay, is less than or equal to the pivot.
The pivot is
Pivot is 5, but the pivot
But
is
till
not in the
now,
right place.
the green, what we are shifting doesn't say about the pivot. It's always 5 is the pivot forever. The green,
Correct.
what we have marked is not a pivot, sir.
No, the green is not the pivot. So what the green is telling you is that everything from the green to the left is going to be under the pivot, below the pivot. That is all the green is telling you. Now what you want to do is you want to swap this, push this pivot and place it in the right place so that everything to the left of this green is not the pivot. Finally, we want to achieve this state where green points to the pivot. Okay, so any confusion here so far?
No, sir. Oh, the pivot's position is not changed. The green pointer wasn't pointing to the pivot.
No, yeah. So pivot's position doesn't change right until the end of the partitioning process. So pivot stays put at the start. Okay, you only move the pointers and swap wherever necessary. And right at the end, what you do is you move the pivot. After you have partitioned it, based on the pointers, you move the pivot. Okay, so what I'll do is I will make these slides available to you all, so you can run this 1 or 2 times and until you get convinced. All right, so
again now
Sir, can you repeat how the pivot has been shifted before 3?
Pivot has been shifted before 3. See, till which part did you understand? Till this, is it clear?
Yes, sir. It is clear that leftmost is the pivot, and everything, this right pointer, we keep on changing and we keep on swapping. The moment it is less than the pivot, then it is, and this I have understood.
Okay, so now everything to the left of green is, by left of green, I mean including the point at which green is pointing to. Everything from this position to the left is less than or equal to the pivot. Everything to the right of green is greater than the pivot, right?
Yes, sir.
Okay, now what we finally want is that I want to move the pivot in such a position so that everything to the left of the pivot. So see, this green and red are what I introduced. They are not actually there in the list, right? So these are green and red. The list doesn't know what it is. Finally, I want this kind of a position where everything to the left of this is less than the pivot. Everything to the right of this is greater than the pivot. That is what I finally want. So to achieve that, what I do is I swap the current green pointer with the initial value. Initial value, remember, is the pivot so far. So I do this swapping.
So that means the last, like this, the smallest element is swapped with the pivot element, is it, sir?
Not necessarily the smallest element. In this case, it happens to be the smallest element. But whatever element is there at the end of this left half, right, or left part,
of left half. Yeah. Okay.
That element is swapped with the pivot. So maybe what I can do is, if you add an arrow, if you add a line here, so just give me a second. Yeah. So what this does is, everything from this line, right, this divide, so call this a divider. Everything to the left of the divider is less than the pivot, or let's forget the pivot. Everything to the left of the divider is less than 5. Everything to the right of the divider is greater than 5. Now I want to reach a stage where I bring the divider, I bring the element 5 here. Okay, so how do I do that? I swap it with the rightmost element in my left part of the list. This is the left part of the list, right? I bring the first element to the last position in the left part.
So, sir, what we have done practically, that this green pointer we kept on moving and swapping. bringing all the numbers less than or equal to the pivot to the pointer, and whatever, and run through the whole list actually.
Yeah.
Then whatever is the last position of the last number at the pointer, we will swap that with the pivot, and then we'll start comparing and doing everything again till you actually reach whatever you want to do.
Exactly. Yeah. So this, yeah, the last element of the left list or the left part is swapped with the pivot. So that is why you get 2, 5. Earlier it was 5, 2. Okay. So I hope it's somewhat clear now. If not, I think if you just go through it once more, it will be clear. So now you recursively do this for these two parts of the list. Okay, is that fine? Okay, so for those of you who have understood, yeah. Right, so for those of you who have followed so far, there is also another partitioning scheme, so which was actually introduced by, this was the scheme that Tony Hoare used in his actual description of the algorithm in 1961. Right, for some reason, there is a perception that this is more difficult than the earlier one, which is called Lomuto scheme, but I don't know. So what I will do is I'll quickly run through this for the benefit of all of you here. Right, you can follow whichever you want. So what this does is very interesting. It maintains the same left and right pointers. Okay, so everything to the left of this pointer, left pointer, is less than the pivot. Everything to the right is greater than the pivot, and everything in between is something that we have not yet sorted out. Okay, so that is the basic idea. So if you look at this, I first look at this left pointer. 5, it's the pivot, so it's less than or equal to the pivot. So I move this pointer to the right. Okay, so now 9 is greater than the pivot. So I stop looking at this and I move to this. Okay, as far as the right pointer is concerned, 6 is greater than 5. So I move this to the left. Okay, so far, is it clear?
Sir, can you repeat the last process?
So what is happening is, I look at these two pointers successively, right? Or alternate, what's the right word? One after the other, okay? So first I look at the left pointer. My condition here is this. If the element that I'm pointing to is less than the pivot, then I move it to the right. Less than or equal to the pivot, I move it to the right. If it is greater than the pivot, then I come to a stop, right? I don't know what to do. Okay, same with the right element, or slightly different with the right pointer. If this element is greater than the pivot, then I move it to the left. If I come across something that is less than the pivot, I don't know what to do, I stop. Okay, so let's run through this. You will get to see what's happening. Now we are at a fix, right? I can't move this to the right. I can't move this to the left.
So 5 is our pivot here.
5 is our pivot, yeah.
Okay.
Okay, so now what we do is, just like the previous scheme, we swap, right? I'm at an impasse, so I swap 2 and 9. Okay, now I continue the process. So the element 2 is less than the pivot, so I can move this fellow to the right. Since this is greater than the pivot, I don't know what to do, right? So I stop, and now I look at the right pointer. 9 is greater than 5, so I can move it to the left. Sorry, I can move it to the left. Now again, I'm at a, yeah.
Why, sir? Sir, since it is greater, so we have to keep it in the right only, na?
So see, these are two different pointers, right? So if the right pointer, if you find an element which is greater than the pivot, you are going to move this to the left, because our idea is everything to the left of the green fellow should be less than the pivot, and everything to the right of the red fellow should be greater than the pivot. Okay, 9 and 6 greater than 5, so this is fine for me. 2 and 5 less than or equal to 5, this is fine for me.
Okay, the pointer has moved to 3 now. The right pointer is.
Yeah, it has moved to 3.
Okay, sir. Yeah.
Okay, now we are again at a position where we need to swap, right? This is greater than the pivot, this is less than the pivot, so I swap 3 and 8. Okay, now what happens is that I continue. So 3 is less than 5. I can move the green to the right. Mind you, we now come to a situation where both of them are at the same location in the list. Okay, now I can't move the green to the right because 8 is greater than 5, but I can still move the red pointer to the left. Okay, at this stage I stop. The moment the pointer switch, then what I know is,
Can you just repeat once? Both the pointers were pointing to the same thing.
yeah, so what happens is now both point to the same thing, right?
Yeah.
So everything, so my green is here. So green is pointing to 8. 8 is greater than 5. So I can't move green to the right. I have to stop green. However, 8 is greater than 5. So I can move red to the left.
Okay.
Okay. Now everything to the left of green, 3, 2, 5 are less than or equal to 5. And everything to the right of red, 8, 9, 6 are greater than 5. So I stop the scheme. So I stop the partitioning. Okay, now what we do is very similar to the earlier step. We have to swap 3 and 5. So I move my green pointer here and do the swapping.
Sir, what is the condition for this swapping? I mean,
so the condition is everything to the left of the green pointer, right? It should be less than the pivot.
Okay.
So I move the pivot one step to the left. Sorry, I move the pointer one step to the left and then swap. So swapping is very similar to placing the pivot at the right location is very similar to the earlier partitioning scheme. Okay, so this is what Hoare used in his original paper.
Excuse me, sir.
Yeah.
Sir, so this swapping is done after when the 2 pointers cross.
Yeah.
We shift the green pointer towards the left and then swap the positions.
Exactly. Yeah. So when they cross, then you know that you have essentially partitioned it. So the only thing remaining is for you to place the pivot at the right place. So you move the green pointer to the left and then swap.
Yes, sir.
But then it has to be, that means we do this once, then we change the pivot and we do this again. Is it like that actually?
Now it's very similar, right? So the partition, once you partition it, then you repeat the process for the two parts. You do this again for 3, 2 and then again for 8, 9, 6. Okay, so this whole partition is just extra stuff. If you want, you can look at it again, but it's not like binding on you to know this. This is just extra stuff. Okay.
Sir, is there a reason why the green pointer was moved to the left after they were in the same element? Because once both the pointers are in the same element, we wouldn't have to check to the left, right? So does it have any extra use when it comes to implementation?
Yes, right. So if they are at the same position, you are still not done, no? Because
yeah, but it would automatically mean that all the elements in the left of this are equal to or below the pivot, and the ones on that and right.
So everything to the left of green, I know. Everything to the right of red, I know. But what about this 8? About this 8, I don't know, right?
Yeah, right.
Right. So that is the reason why you move this red once more to the left and then you stop. So you stop exactly when they cross each other.
All right. Yes, it's clear.
Okay, so this is.
And how will this be different from the Lomuto one? Is there any difference when it comes to practical implementation of this code?
Yes, yeah. So apparently this is 3 times faster than the Lomuto scheme. So the reason we use the earlier scheme is because for whatever reason, textbook writers claim that that's easier to understand. Perhaps it is, I don't know. But that this whole partition is faster by not. So it's still O of n. So if you look at the complexity, it's still O of n, but the hidden factors are there, right? So when you bring that into consideration, this is faster.
Okay, sir. Thank you. And can the code for this be shared?
Yeah, sure.
Thank you.
All right. So that is core partition, that brings us to a close as far as sorting algorithms for this course are concerned. Okay, so one important point is this, that any sort that uses comparisons, right, where you compare two elements, which is greater, which is lesser, that is called a comparison sort. Okay, all sorting algorithms we have seen so far all are comparison sort, selection sort, insertion sort, merge sort, quicksort. All of them, if you actually think about it, they are comparing two elements. Is x less than y? Is L of 1 less than L of 2? Something like this is happening. And there is a very well established result which claims that the worst case lower bound, right? The lower bound. Till now we have been looking at O of log n, n log n upper bound. See, the lower bound for all comparison sorts is n log n. So you cannot do better than n log n when it comes to comparison sorts.
So, but we always need to compare when we are sorting, right? So why the name comparison sort?
So we not always, right? For example, in week 2, PPA 2, I think there was one question where you had to sort numbers, and you knew that all the numbers of the list will lie from 0 to k, right? So in such cases, what you can do is there is what you did there is actually a counting sort, right? So you can look this up in either Wikipedia or wherever. This is not a comparison sort. So you can use some things like this when you have a suitable kind of a list, right? But
sir, I'm referring to the one where the dictionary was used to take count of all the elements present, and then it was printed according to the order.
Yeah, exactly. So that is a linear sort, right? So you actually sorted in linear time.
Yes.
Right. So okay, so that is regarding quicksort sorting.
So here in second point, you have used worst case lower bound.
Yeah.
Right. No? So do we have worst case upper bound as well, right?
Yeah. So the worst case upper bound for all of, not for all of them, but for say merge sort is n O of n log
Correct,
n.
n square or something.
Yeah.
But why we are not calling it best case lower bound?
See, best case lower bound could even be O of n, right? We don't really bother about the best case, no. So, for example, if you look at insertion sort, you can, the array is already sorted, then you can do it in linear time. You don't need to take off. You don't need n square steps, basically.
Okay, okay. So suppose just we are talking about merge sort or quick sort. So best case lower bound will be n log n.
Best case, not best case lower bound.
Okay.
So worst case lower bound will for all comparison sorts, right? So what we are meaning by this is that it's a lower bound, right? At least, I mean, there's no way I can do
You
sorting
cannot go below this.
Yeah, exactly.
So that is the best case. Means, no?
No, not best case. It's the worst. So see, for both best case and worst case, you have some running time, T of n.
Okay.
Okay. And what we are saying is that, so maybe like, I'll just go to this. See, there is a best case running time for an algorithm. There is also a worst case running time for an algorithm. So what we are saying is that this worst case running time is omega of n log n. This is what we are saying for any comparison sort.
Correct. That was my understanding. So when you put both together, okay, when we say lower bound, that is the best case, worst case scenario, right?
Yeah, worst case scenario, lower bound.
So lower bound means like it is like the shortest time that algorithm is taking, right?
Okay, so what we mean by a lower bound here is that it's not the shortest time. It's that what we are saying is that the algorithm will take at least this much time, right? So that's what we mean. So if you want it mathematically, then what we are meaning is TW of n will be greater than or equal to n log n, right? Or some constant times n log n. So C into n log n. This is what we mean. So in the worst case, this will take at least n log n time or some multiple times n log n. Okay, so that is sorting, and I hope there are no other questions. Now we'll go to lists. Okay, so
sir, one small question, sir.
Yeah.
Sir, actually in this also we ended up, like practically the first one we compared with so many numbers. And then later on also we were comparing.
Yeah.
So how is it better than, what we were doing, nested loop in which, you keep on finding the minimums and keep on placing them in first place? Because this also seems to be, as involved because you keep on checking with comparing with each number.
All right, that's a good question. So what you're essentially asking is, how is this linear is what you're asking. So this, or how is it n log n, or why do you say it's n log n when I'm doing so many comparisons?
Yes, sir.
Okay, so for that we need to understand the complexity of partition. So see, I'll again go to the math part of it. So what you're essentially doing is, if you have a list of size n, its running time, let's say, is t of n, you are dividing it into two parts, right? And you're recursively calling it on each one. So this is 2 times t of n by 2. Okay, and then I say it's this partition, I say it takes O of n time. So if this is true, then I can say that t of n is n log n. So do you agree with this? Is this
Yes,
clear?
sir.
First of all, is this equation clear to everyone? So
Sir,
this is something I want to know.
Sir, how? No, sir. But 2 into t of n by 2, sir. How did this equate to n log n? I mean.
Okay, so you all, so I mean, not you all, but you don't get why it's n log n. Is that right?
Yes,
yes,
sir.
sir. Like, how
Can
is
you
this?
please explain with some examples, sir?
Okay, so see, there is a.
So can you explain how is Tn is equal to 2Tn by 2 plus O of n?
Okay, right. So this is so what we need for that is, let's take this case. Okay, so first of all, there are so many things happening here. So what do each of these things stand for is something we need to understand. T of n is the time taken to sort all these elements. Okay, all these, how many are there? 6 elements. So the T of 6 is what we are talking about. Okay, so ideally what Quicksort does is it partitions them into 2 halves. So it gives you these 2 parts, right? So of size n by 2 each, roughly. Okay, so this will be like, forget about the difference in, so this is 2, this is 3, but 6 by 2 is roughly 3, right? So I mean 6 by 2 is 3, but the 2 parts are roughly of size 3 each. So if you choose the pivot appropriately, you will get 2 parts of equal size. Is that argument okay?
Yes, sir.
Okay, then I recursively call Quicksort on each of these parts. Therefore, I get this 2 times t of n by 2. Okay, so this 2t of n by 2, if I hope it should be clear. Now you can ask, what is this O of n doing?
Yes.
Okay, O of n is the time taken to partition the list into 2 parts, such that left part is less than pivot, right part is greater than pivot. So the thing that we need to understand basically about Quicksort is, why is this linear, or why does it take O of n time? If you understand that, then you understand Quicksort. That's why in one of these slides, I had mentioned that the heart of the algorithm is the partition operation. You don't need to understand anything more than the partition. If you understand partition, then you are set. Okay, so is this clear so far? Why this part is coming out to be 2t of n by 2?
Yes, sir. We are
Yes, sir.
partitioning. That's why n by 2. And since the partition is taking 2 times, like left and right, therefore is it getting multiplied with 2?
So the reason it's getting multiplied with 2 is that, see, where is the partition? Once you partition, these are still unsorted, right? So 2, this is probably sorted, but 986 is unsorted. So you have to run this, you have to run the procedure quicksort on these 2 parts again. Okay, so here I think we need to write some code. Code is easier. So if you call quicksort on a list L with 2 parts, right? Left part and right part. What it's essentially doing is it's partitioning. So I will call a partition function on this same thing. It will return one pivot, right? Index of the pivot. So I will now run quicksort on this list L with indices L comma P minus 1, and I will run quicksort on L comma P plus 1 comma R. So roughly, right? I may be wrong about the exact indices, but this is the skeleton of quicksort.
Yes, okay, sir.
Okay, so now do you see why if this is T of n, then hoping that my partition divides it into 2 equal or 2 halves, right? Then of size n by 2 each, then this will take T of n by 2 time. This will take T of n by 2 time. And that's why I get this 2T of n by 2 here.
Yes, sir.
Okay, now the whole question is how much time does partition take? That's the whole question. Okay, if you are able to solve that, then we are set. And the claim is that I claim that it takes linear time. That is, as many elements are there in the list, that many times some constant, that is the time taken for partitioning. Okay, so that is very simple to see. So you start, let's go to this Lomuto scheme, which we are sticking with in this course. Look at the right pointer, what is happening. Okay, I'm sorry. Yeah, so look at the right pointer. You are comparing the right element at the right pointer with the pivot, right? So you are making one comparison here. Next, you are shifting it. At this element, you are again making one comparison. Here again, you are making one comparison. But once in a while, you are swapping. That doesn't matter because swapping is again a constant time operation. Again, you are making one comparison at element 2. Again, you are swapping, but as I mentioned, swapping is still constant time. Finally, you are doing one comparison with 6. Okay, so you're doing a linear, the number of comparisons that you do is proportional to the number of elements in the list. So you're actually not doing so many comparisons. You're only doing roughly of the order of n comparisons. Now, is that clear? Because
Yes, sir.
Yes, sir. Yes.
Okay, right. So that is why you have O of n. Now, if you want to see how this becomes n log n, you could do this whole process of unrolling the recursion. So this is n by 2 square, right? I again halve it. So n by 2 will become n by 2 square. So I'll just replace O of n with n. It is convenient. So this will become what?
So won't there be 2 square outside, sir? 2 square T of n by 2 square?
Yeah, you are right. So this will be
Each time we are doing it, 2 to the power of n situations will keep occurring.
Right. So this will be 2T of n by 2, right? So, okay, let me write it slightly elaborately. This will be 2 times 2T of n by 2 square plus n by 2, right? Is that clear? Is this step clear?
Yes, sir.
Yes, sir.
Okay, so this is what? This is 2 square T of n by 2
N
square.
again, isn't it?
So n by 2 becomes n by 4. I'm just writing it as n by 2 square. Okay, so n by 2 plus n. So if you keep unrolling this, you will hit one 2 power k. Yeah,
N
that
plus
too
n.
will also.
So it becomes
sorry.
n plus n to n.
This will be just n. Yeah, this will
It's
just be
just
n.
2n.
Yeah, this will just be 2n. Sorry. Okay, so if you do this, let's do it one more time. So 2 square into 2t of n by 2 cube. Okay, plus n by 2 square, right? So let me know if I'm going wrong somewhere.
It will be 3n, sir. Just 3n, isn't it?
Yeah.
So it will be n plus 2n.
Yeah, so this will become 2 cube t of n by 2 cube plus 3n, right? Is that right?
Yes, sir.
Okay, so now what we do is we keep doing this for several steps. We'll finally end up with some 2 power k, and this will be 1. I'm assuming that n is a perfect power of 2, right? Let's say n is 2 power k. Okay, so I will just state it here. This doesn't invalidate whatever we are doing. So assume that n equal to 2 power k. Okay, so 2 power k, n is 2 power k means this will become 2 power k, n by 2 power k by 2 power k will be 1 plus this will be k times n, right? Is this clear so far?
Yes, sir.
Yes, sir.
Okay, so if n is 2 power k, then what can we say about k?
Log n to base 2.
Right, so log n to base 2, I'm ignoring the base because in computer science usually it
Computer
is
science, yeah.
base 2, right? So k is log n. So from this what we get 2 power, so 2 power k is basically n. Okay.
Yeah. Yes.
T of 1 is 1, right? It takes unit time for sorting one element array. So you get k is log n. So log n times n. So I write it as n log n, which is nothing but O of n log n, because n is a smaller thingy compared to n log n. Okay, is this
Yes, I got it. Yes.
okay? So this is very important. So if you unroll the recurrence for t of n is 2 t of n by 2 plus n, you will end up with t of n being O of n log n.
Sir, just a doubt. Whenever
Yeah.
we are writing a code, we should also simultaneously keep in mind these kind of worst case situation or best case in our head when we are creating a code, or we just ignore it.
Perhaps not as you are writing the code. That might be a bit tough. But say there are two ways to do it, right? One, you either have a very clear idea of your algorithm that you want to implement, and then you just go ahead and implement it, knowing what the complexity will be beforehand. Or you write your code and then analyze the complexity. There are like two ways to do it. The way you are suggesting might be a bit tough, right? As you are writing, trying to find out what is the complexity might be a bit tough.
No, because every time when the teaching happens in a lecture or anywhere, they always concentrate on it takes so much, even in practice assignment, few questions. So I was wondering whether as a student, I need to concentrate on that factor simultaneously.
Yeah, so that is also important. So in these
Yes,
questions, right, we'll look at it so that,
yes,
right. So that is regarding Quicksort. Yeah, now we'll quickly go through lists.
Sorry, sir. I have one more question.
Yeah.
So I have question regarding like the code that sir mentioned and regarding the Python code. So
Okay.
what I didn't understand was like when we recursively call the quicksort, so we are sending the list,
right,
and the start and the end pointer. But I don't understand like list is getting sorted, but whenever the method is sorting the list, so will the same list is getting sorted, or like the values are copying when we call a recursive method?
This is a
So I'm
good
getting
question.
confused
Yeah.
regarding that.
Okay. Once again, I just document that we have done this so that later on we can directly copy from this. Okay, this is, can we underline in this software? Yes, we can, but it doesn't look good. So we'll just copy, call it as topic 1 during this session. Okay, no, we don't need this for some more time. So what you don't understand is the list actually getting updated or not, right?
Right.
Okay, that's an important point because so see, I'll just copy my I have an implementation of this Quicksort, so I just copy it for, if we have time we could actually write it down step by step, but unfortunately we don't have that much time.
Yeah, no problem.
So I will pull this here.
Just to interrupt.
Yeah.
While we were deriving n log n complexity,
right,
there was this n plus n log n.
n plus
So
n,
we are,
n plus n log n. Yeah.
So we are ignoring n.
Yeah, we are ignoring n here. Yeah. We are ignoring n because n log n dominates n. That is the reason we are ignoring it.
This happens just because n will be greater than 2.
Is because n as n becomes large, right? As n becomes very large. So
exactly. So that is the because theoretically it may not be the case.
Right.
But yes.
True. Yeah. Okay. So going back to see, this is the code for Quicksort. Okay, using this our partitioning. Let's just stick to this partitioning scheme. So what has been done here, you might find interesting, is that I have not used the list. I have not called the list L anywhere. The list is actually that is getting sorted as capital L. Okay. Okay. First of all, do you understand this code? I just copied it, so it might not be quite clear. Who asked this question?
Yeah. So yeah, I asked. So yeah, code is like clear to me.
Okay. See, your question is where is L getting updated, right? Is L even getting updated?
Right.
Okay. So here we use the property that that has added. We are using the property that lists are mutable, right? So this is very important. So we are using this property, and that is the reason why you actually the list L is getting sorted in place. So if you want a quick example of what I mean by that, let's write a simple function called do something on. I don't accept any arguments, but I am going to modify a list. Say I'm going to swap the first and last elements. Okay. So this is the list, and then I'm saying L equal to, and then I call do something. Now, what do you think will happen? If I print L, ideally it should throw an error, right?
Right.
But if you notice, what happens is that
So why would it show an error? Because it is just swapping, right?
It is swapping, but I have not passed the list L to this function, no.
Okay, yes, sir. Yes, sir.
So, I mean, if I have to pass the list to this function, then ideally this should throw an error, but let's see what happens. Collab takes so much time. Yeah, so see, it has swapped correctly, and on top of it, it has not even thrown an error, right?
Yes, sir.
Right,
So
right. Maybe if we change the name of the list to from L to something else, it will throw an error.
Right, true. If you change the list name, it will throw an error. But this works because lists are mutable. So that is, and I don't actually need to explicitly pass them to a function. Okay, if you understand this, then you understand what Quicksort is doing. I am not passing L at all, but it's still working.
So as an extension, I can't do this for a tuple, right? Or a tuple, I won't be able to do this.
Yeah. Because it is immutable, so you won't be able to do this.
Okay.
But however, so it's not just about immutability. Good that you raised this point. Okay, I don't need a separate code block. I can work with this. Lists are mutable and they are also like, so maybe I'm not expressing it clearly. It's not just about mutability.
It's kind of globally available, is it?
Yeah, exactly. So as long as I
can't do a pop of tuple or something.
Exactly, yeah. So it works not just because lists are mutable, but because, as you said, it's available globally, and when I can change, and the reason why I'm able to change is because of its mutability.
Right.
Okay. So this needs some getting used to. It can be tough initially, but yeah. Okay, where were we?
Got your point. Yeah, thank you.
Yeah, so we were doing lists, right? Yeah, lists.
Sorry to interrupt you.
Yeah.
Just wanted to know, for all the programming tests, if I practice all these merge, sort, recursion, all those things, will that be enough? Or I believe in only practice because I'm very new to coding. So
okay, so
for this PDSA, the more this merge, sort, all these things, if I practice the same thing again and apply it, will that be enough? Or
see, PDSA, actually there are two things to PDSA, right? One is the DSA part, and the other is the programming part using whatever DSA you learn.
Yeah.
So this course, I would say, is 75% DSA, 25% programming. Okay, because the emphasis here is not so much on programming, but on understanding what algorithms are. Yeah, that is the focus of this course. That's why you have like 2 quizzes and 1 NSEM, which are all theory, and only 1 final programming exam.
Okay. Thank you.
Sir,
Yeah.
Sir, like in understanding the algorithms, I don't have such problems. Like they seem quite like I grasp them quite in an easy way. Like, but sir, my main weak area is that I'm quite weak in coding. So, sir, how do I improve it? Like, sir, I am thinking of a concept, but when it comes to implementation, there where I get stuck. I mean. So how do I improve this?
I am also in the same level. Whoever spoke, my three.
Yes.
Logic it comes, but when I start coding, I get really scared, and everything stops. Everything throws error.
Exactly.
I am so scared of it now because understanding. I understood merge sort, quicksort. The logic analysis is clear, but when it comes to applying it, there are times where I don't even understand the question. I mean, it's pretty tricky.
Exactly, sir.
That's the problem I have.
Yes, sir.
Okay. All right. See, are you able to code all these starting right from insertion sort, selection sort till quicksort? Are you able to code each of these things properly without looking at the lectures?
No, sir. No, sir.
Okay.
I am able to understand the concept, but not coding.
I am just practicing the merge sort, whatever was taught in the class. Same thing I'm writing, and then trying to implement it where I go terribly wrong. And I had to ask some of my friends and students.
All right. So see, this comes with practice, right? point taken, it is certainly more tougher than Python course, right? Because there the emphasis was only on learning how to program basic things, but here you need to do a 2-level thing. So for example, if you take this partition function is not at all trivial. It's very tough to write. Okay, so I'll just put it on record in case that is what you are wondering, which is that this probably supposed to be easy, but I'm taking so much time. Trust me, writing this partition function correctly is not easy at all. Okay, so I would say spend more time on being able to write this without memorizing, right? That is the skill. Ultimately, that is the skill that you have to pick up, right? You must not memorize the partition code. You must, okay, if at all you have to memorize, you can memorize the algorithm that is there. And somehow, through multiple attempts at writing the partition function, you'll be able to write it. But it will take time. So, and unfortunately, I don't have any better suggestion to give. But if you are thinking that this is happening only to me, or I am only struggling and rest of my peers are progressing, please don't, of course I'm not saying you compare yourself, but please don't think that way. This is highly non-trivial. So for example, getting the partition function right is all there is to Quicksort, right? If you look at Quicksort, it's only 6 lines and the bulk of the effort is in partition. So this is just an example, but it will take time and you have to work at it. There's no other better solution I have right now.
Excuse me, sir.
Yeah.
So is there any logical reason why Hoare technique is 3 times faster than Lomuto technique?
So this is something I haven't actually explored myself. This is just factual knowledge that I have, that partition, this Hoare is 3 times faster. Maybe we can study it.
Maybe it's due to pointer moves from both sides in Hoare technique.
Probably, yeah. The claim is that it performs fewer comparisons. I haven't checked it out myself, but it should obviously be true. But I don't know why exactly. But what you said makes sense. Yeah. Right. So before we get to that, what I would like to do is we'll finish lists also.
Sorry.
Yeah.
It's regarding the ability of the list which you mentioned.
Yeah.
What you said is list is modified. In the function you are.
Hello. Sorry, your voice is breaking for me.
Yeah. Can you? Audible?
Hello. I lost you in between.
Am I audible now?
Yeah.
Okay. It's the mutability of the list which you showed.
Right.
Now there, what is happening is in the function, you are not sending the list, but still the list is getting modified.
Right.
Right. But this is contrary to what was said in the lecture, where it was said that, if you modify the list in the function, it will not change the things.
So, for which one are you?
In the lecture, which is lecture number 23. This is difference between list and array, 3.5.
Oh, okay.
Right, where the differences of list and arrays were discussed, 3.5 and
Okay.
6.
Okay.
So why is it happening? Still, I couldn't able to understand that you are not passing the list to the function, but still the list is getting modified.
See, let me take something which is not a list first, which is, say, some variable, say x, which I define. So there are 2 things happening here. One is x equal to 5, right? So do you think this code will work properly? Error free. Is this code error free?
Well, it should not, because you are not passing anything to the function.
Okay, so let's try to run this. Let me
Yeah,
remove
but
this.
it works.
It works, right? So yeah.
So X is acting as a global variable. This means.
Yeah. So X is actually global here, and it is global, right? Because I haven't defined it precisely.
But then it's a
within
problem because if I can write down another function which modifies X.
No, that is where we come to the immutability part. So there are two things. Here, X is an integer which is global. Okay, so I can print it, I can do anything, but as it is immutable, okay, as it is immutable, what I can't do is I can't do X equal to 5 or say X equal to say 1. Now, if I run this, I'll get what is called an unbounded local error or unbound local error, meaning local variable X is referenced before assignment. Okay.
Yeah, but with the list, this was happening.
Yeah, with the list, it happens because in addition to being global, it is mutable.
Okay.
Right. So there are these two things. It can be hard to understand first.
So that means I can write down two functions which keep on modifying the list without even passing them.
Yeah, without even passing it. Only care that you have to take if you want to achieve that something like that is you shouldn't reassign the list anywhere. So for example, if I do L dot append, it will change list L.
Yes.
But if I do something like this, okay, then let me print inside function. This is the list, and let me remove this append, or let's have the append. It's fine. Outside function. So if I run this now, yeah, I get the same problem because I'm here. It becomes a local variable. The moment you have an assignment statement, it becomes a local variable. So as long as you don't assign any value to L, it remains global.
No, but when you are interchanging the elements of the list, then it didn't created the problem.
Exactly, because what you are doing is you are only modifying the list L in place, right? You are.
So if I want, I can multiply any scalar to any element in the list.
You can do anything you want with L. It will not throw an error.
Okay, as long as I am not changing the dimensions of the list.
As long as you don't reassign the list L with some new value. So for example, moment L comes to the list.
If I want to say I have a list of 3 elements, say
okay,
global one, and I want to multiply a factor of 2 to the second element.
Okay.
So will that work?
Yeah, that will work, right? Because the object L you are not changing. So the object L it still remains the same. What I mean by object L is that each object in Python has some identity. So
right.
So if you print the identity of L, the identity will be the same. So if you look at this, it's 42560. This is also 42560.
Okay.
So you are modifying the same list.
But then it is problematic because accidentally I can do something. I can write multiple functions, and then it could happen that I have used the same name, and they keep on modifying the list.
Yeah, it is both problematic and useful, right? So here, for example, it was useful because I didn't have to explicitly pass L for in my quicksort function. I could just get away with not passing it. But as you said, it's problematic if you use it.
If I have multiple functions, say.
Right. Yeah, you could potentially misuse the facility.
And you can't even figure out where it was changed.
Yeah, true.
Okay. Is there any way by which it can be stopped explicitly?
Yeah, I mean, you have to accept and return. So you could always do that. But even then, right, even if you accept something like this, let's say P, and you're only modifying P, you will still modify, you will see that you will still modify L. For example, let me do print L. You hope that L remains 1, 2, 3, right? After this.
Right.
But what is this? Okay, I didn't pass L. But it turns
here
out that
L will be modified.
L is modified.
Yeah, here it would be because you are actually passing L.
Yeah, but I'm only changing P, right? If you look at it that way.
But that's a local variable.
Yeah, but if I change it from a list to a normal immutable value, the outside thing will not be affected. Right?
Yeah, if I don't return.
Right, right.
Yeah, if I don't return, this will not. So this is special about the list. They are mutable, but other variables are not.
Yeah, yeah.
Okay.
Okay, so now...
sorry, can I ask another question?
Right.
There was a statement which was repeatedly said in the lectures, and I couldn't able to understand is that generally recursive algorithms are a bit slower than the iterative ones.
Right, yeah.
Why is it so?
So, see, recursive algorithm internally, right? So internally it maintains, each recursive call is maintained on what is called a stack. So you would have, I think if you have seen lecture, week 3 lectures, you would have come across this notion of stack, right? So at the outset, it seems like it's just a single line of Python code, but then internally the language has to maintain the stack, and it has to suspend function calls. It has to do a lot of under the hood work in order to get this recursion working. Okay, that's why we say that iteration is faster than recursion, because in iteration it's very simple, right? You just go through a loop one after the other, one iteration after the other. But in recursion, there is a lot of support, backend support that is going on, and therefore it's slower.
Okay, thank you. Thank you.
Yeah. All right, now finally we'll go to lists. Okay, so I think list, most of you know the basic idea you have. It's different from an array in the sense that an array is like a contiguous block of memory, right? One after the other. Whereas lists are like scattered. So all that links two elements of a list, two nodes of a list is this arrow here, right? So you always start with the head, and then you can trace these arrows and go from first element to the last element. Okay. And in our course, the convention we follow is that an empty list is just one node with the value none. Okay, so yeah, so does anyone have any questions on lists specific? Yeah, some of you wanted to know certain things about lists, right? We can probably discuss that first. Any specific problems with lists? Okay.
Yes, sir, that insertion an element in the list and deletion.
Okay, so yeah, deletion, we'll come to it. Insertion, I haven't added any slides, but that should also be, yeah. So let's first look at append, right? When we append, what we do is there are several scenarios to consider, or maybe one or two scenarios to consider. One is when the list is empty, right? When you want to append to an empty list, what you do is you just change this none to 7. Okay, and that is your append operation. All right, so maybe since many of you are talking about the code aspect also, let's do this. Let's parallelly code. Okay, so I define a node to be the following. What is a node? Node has some value v, so some value okay, and it has a next, which is none. Okay, is this clear? First, what we mean by a node?
So
Yes,
can
sir.
we, like say, like, why did we write the self dot value equals 1 and self dot next? Is it an empty node or something?
Yeah, so whenever we initialize a node, so we'll initialize a node as follows, right? So say L equal to node of, so this will be an empty node. So if I call this, it will look something like this, none, with nothing, no, this next being none and value also being none. Okay.
Okay, sir.
Now what we do is, first thing to ask is, how do you know if a list is empty? Okay, list is empty when the value is none. So I just write this as self, I just write this as follows. If my value is none, then it means the list is empty. Okay, so let's check if this works. Is L empty? Yeah, L is empty. Okay, so empty is clear. Now, how will you append an element? Okay, so we'll go case by case, right? So this is how, so for those of you who asked about how do I go from logic, or how do I go from understanding an algorithm to coding it, I need to append an element. What do you mean by append? So let me take, say, a case like this. If you have a list, say 598, then you want to append this element 7. So how do you do this? Okay, so the algorithm is this. You start
Just
with 5.
before that, can I ask you one question,
Yeah.
sir? For this link type of list where a part value is stored, another part the address, the location where
Right.
it will going. So you start coding in this, means taking the class and object.
Right.
Why is that is? Because of this address to attain the address part?
Not just that, yeah, that is one thing, but you model your node as an object. So in fact, everything in Python is an object. And if you look at this object here, this box having a value and something dangling here, right? So this I model it as a class. So this box with a value and something popping out of it, I call it a class node with value being the object inside the box, the number inside the box, and this arrow from one object to another object that looks just like it, maybe with a different value, that I call next. So I model it.
So basically,
yeah,
each and every node is an object of class.
Exactly. Yeah. Every node is an object of class, capital NODE.
And how it is different with the list? So far we learned any element of the list having a value and the corresponding one indices. With these two, can't we do this? Means why we are shifting from that to in this class mode? I am just asking, sir.
Yeah, so you can do that, but they are not in some sense primitive operations. So we'll come to that. So you'll so your question is why can't we just use Python lists, and why do we have to define our own version of lists, right?
Correct, sir.
Okay, so we'll come to that. You'll see that Python lists is not actually a list. If you have watched the lectures, you will know that Python list is closer to what we call an array. And for that reason, we just to demonstrate that this is what a list is, right? A list, okay, a linked list, as we call it. Maybe it's a better term rather than calling it just a list. But yeah, we'll come to that.
Okay.
Okay, so how do you append now? You started this node. You want to append this 7 here. One way to do it is recursively, right? So I am at this head and I see that something else is there next to me. So I can't append here. So I go to that particular node following this next pointer. Can I append here? I can't, because there is something else to my right. So I go to the next one. Now I see that there is nothing else next to me. So this is the last, in some sense, the last element in the list currently. Now I create a new node and then I append. I make this attachment node. Okay, so this is the general idea of recursive append. Now, is this clear? Is this algorithm clear? Recursive version.
Yes, sir.
Okay, now what we do is we go and code this up. So what we do, I'll just write that part now. Append self, you are appending a new element. Let's call it V or maybe X. How do you append X? If you followed this arrow business, you ask if the next is there or not, right? So if
Sir, this returned true when we asked that, like when we checked if if the node is empty or not, sir. Why, sir? Because here then when self dot next was none, right? But self dot value is equal to value we wrote, so there was some value, right? So, sir, how can this be an empty list? I mean,
no. So what I meant was, then this is the last element of the list. So see, the basic idea of append is that recursive append is that I append when I reach the end of my list, because append means that, right?
yes, sir.
So
Yes,
the
sir.
whole idea of recursive append is to see when I reach the end of my list.
Okay.
Okay, so it is easier if we look at the two base cases before that. So if the list is empty, meaning if there's only none, then you essentially want append will just be creating a list with 7 as the value, right? So that will be the list. It will be a single element list. So we'll just finish that first. It's easier to do it that way. So if self dot is empty, if the list is empty, then you know that self dot value is none. So you set it to X and then you return. So you end the code there. You end the function there or method. Okay, so let me just create a new cell for this. I don't want to confuse my class implementation with. Okay, right. So this is scenario 1. So scenario 1 is clear, right? What we are doing. If it is empty, you initialize it with this value and you are done. Scenario 2 is what we are now looking at. If it is not empty.
So that means, sir, in this case, we have, so the moment we have added 1, we cannot do anything further with this list, because we've already added 1, it will no more be empty.
Yeah, so see, if it is an empty list, then you want to add 7. Okay, 7 or 1, and that's all. So you want to just append the element 7 to an empty list. That is your goal, and you have achieved that in these 3 lines. Okay, that's why you're returning. You are done. I mean, there's nothing left for you to do because you have appended to an empty list and you are done. So this is scenario 1, which is empty list. Now, what is the second scenario? Actually, I missed it here, but I should have added it. It's actually something like this. This would be your second case where you have a single element list. Okay. So in that case, what do? I ask if self dot next is none, right? See, this is a single element list, right? And there is nothing next to it.
Yes.
So if self dot next is none, so what do? I create a new node with X as the value, and I say self dot next is equal to this new node, and I return. Return meaning I don't want to do anything more than this. So is this clear what we have done here?
Yes, sir.
Okay, so this is
Yes, sir.
Single ton list. Okay, list having just one element. Now we come to this scenario 3. We'll have to rename
But sir,
everything.
the empty list also have the self dot next equal to none, right?
Yeah, and that is, so we don't need to upset that, right? So empty list anyway has self dot next equal to none. We leave it as it is.
Okay.
Okay. So now scenario 3.
Sir, I have a more fundamental question.
Yeah.
If you can just before. So because each node is like an object of that class, right? So
Right.
you have multiple nodes which are just objects of that class.
Right.
Now, if I say self dot is empty, which node object instance of that node am I really checking? Because that's something I'm not.
Okay, that is what this head is doing, right? So for example,
So we have not defined any head or anything in this place, no?
see, this is the head. So when I create a list, and I say this is an empty list. So when I say L dot append, so please remember that I am append. This is not the Python list. So when I say L dot append of 7, and I actually run this, so this will work. I hope this will work for whatever case we have written so far. So if you look at L dot value, so L dot value will actually be 7, and you can print what L dot next is. L dot next will be none, right? So this is the head. So when we create a list with 0 elements and then we initialize it, this becomes the head. So there is only a 1 element list, and this head, or what we call head here, is nothing but L. L is the head here. So
right, and that is something that Python just keeps an address of that. So that object, it identifies as a head, is it?
Yeah, head. So in fact, we call it head. Python doesn't even call it head. So L, as far as Python is concerned, this thing is called L. So phi is L for it. This phi and next together, this object is L for Python. Or if this is, it's more clear, then we can actually call this head. So just to clarify this, in a linked list, the only thing that we have access to is head.
Right.
Okay, and because of the way we link it together, we can use the head to go wherever we want.
Right. So we access the head and then from there just go next.
Yeah. Now that is what we'll be coming to now, where we have more than one element. Then what we do, we can't insert here. So first of all, how do I know if there is more than one element? I look at the next. Is the next none? If it is not none, then I know that there are more than one elements, right? So if self dot next, so I could just use else, but I could just use an else clause here. But let's say since we are returning, we don't need the else clause. Okay. So scenario 3 is more than one element. So what do? I can't append now. So I go to the next node and append there. Now, is this clear? This is all the code is actually.
But when I go to the next node, if it is again, okay, it'll again check if it is none and then it'll just keep moving.
Right.
So basically it is a recursive call.
Yeah, this is the recursive call. This is the recursive append. So this is recursive append. So what we are doing is, when we keep calling next, at some point we'll come against a singleton list. Right? So for example, we start with head, and then we call head dot next. We call append on head dot next. So this will call append again on the next. This will become head and it will call append here. Now when it calls append here, what will happen is this particular scenario will get executed. Okay, so this is what is happening in a recursive append. So let's probably append a few more. And someone has pointed out, we also need to display it. So how do we display? That's a big task on its own. So display a linked list. Okay, so here what I do is I do the same process of starting from the head and walking down. Okay, so for that what I do is I use a temporary head, and as long as my next element is not none, sorry, this is self, right? I'm in the current thing. So I keep going to the next element. Okay, so this might be a bit tricky initially. So let me execute this and show what happens here. Okay, so I note that initially list is empty and then I'm appending 7, 10, and 15. Now I say head.display. Okay, I'm missing out on the last node, I believe. Just give me a second. So okay, so now 7, 10, and 15 are the 3 nodes. So now did you get what happened just now?
Yes, sir.
Okay, right. So what we have essentially done is we have walked down the linked list and we have printed the value at every node. And this is how we this is how we move from the current node to the next node. Right. In the end, what happens is you have to print the last node. So I added this.
Sir, I have a doubt.
Yeah.
So whenever we are appending that element head.append, so is it true that we are also creating the object of that particular class, node class?
Yeah. So whenever you call an append, you are creating one more object here. So it gets created here.
Yeah. Okay. So thank you.
All right. So that is append. I hope you all got what append is. Now deletion is tricky. So deletion is probably the toughest to understand. Again, I just write what we are today, what we are doing. So we want to delete the element X from the list. Okay, so if the list is empty, so this is scenario 1. If the list is empty, then there is nothing to delete. So I can't delete. So what I do is I first check for that condition. If self dot is empty, I don't do anything, right? So there's nothing to delete. So this is done. The next scenario is when there is only one element to delete, right? When there's only one element in the list, right? And that happens to be the element you want to delete. So in all this, all these slides, I will be deleting the element 7. Okay. So if self dot next is none. So let me empty list, nothing to delete. This is a singleton list, meaning exactly one element. So if the value happens to be the X element you want to delete, then what you do is look at the algorithm. I'm just changing this to none, right? It becomes an empty list. So I'm just saying self dot value is none. So are these two things clear?
Sir,
Yes,
in the
sir.
first line number 37,
yeah,
if self dot is empty is the list is empty, you are returning, then why we need this line number 42? So if self dot next equal to none, directly we can assign self dot value is equal to none, because I know there is some value.
yeah, but I want to delete X, right? How do I know if the current, so if the list is if the list is say 5 and I want to delete 7, only if
only
this is equal I will delete,
okay,
right?
Okay. You are checking the condition.
Yeah.
Okay.
So again, I return just to be safe, just to end my code there. So next condition is where it gets tricky. So when there are multiple elements, right, or rather more than one element, right? So what happens when there are more than one element in the list? Okay, so here again you have two, this branches into two cases. Perhaps the element that you wish to delete could be the first element itself, right? So you do that check first. What happens if it is the first element? This might be a bit hard. So what I do is I want to delete 7. Okay, so the list now starts from 9. So this is a bit tricky. What you do is you first swap 9 and 7, and then you make 9 point to 8 directly. In that process, 7 gets deleted. So did you follow that?
Repeat, sir, once more.
So you want to delete the first element in a list, which is having multiple elements. So what you do is you finally the list you want is this, right? 9 pointing to 8. Okay, and this is the list you have. So what you do is you copy 9 to 7. So there is no way I can delete myself. See, I am calling head.delete, right? So I can't. This is the problem that Professor mentioned while inserting also, that you can't delete yourself. You can't make yourself point to something else suddenly. So what you do is you copy 9 to 7, or you exchange, and you make 9 point to 8. In that way, 7 gets deleted. See, what you want to preserve is what? You want to preserve the link from 9 to 8, right? So you do this kind of plumbing where you want 9 to point to 8. So you make this 9, and then you make this 9 point to 8. In that process, 7 will get deleted.
Sir, why can't we make 9 as a head and just remove the link
that
from
is the yeah, that is exactly the difficulty that Prof would have mentioned. That, see, what you want to do is you want to delete 7, right? You want to delete the first node in the list, but how will you make? So I am calling this from this object, right? So I am calling delete from this particular object. So whatever I do, I have to do with this particular object. I can't make 7 suddenly can't become this object 9, or rather this container cannot become this container. Okay, I can't make this the head. So whatever head is given to me, I operate only on top of that. Maybe I can add nodes to this, right? But I can't make myself become some other object altogether. Is that clear? I mean, that can be confusing.
So to give a crude analogy, if it's like a snake, you can't cut the head off of the snake and then it will just cease to exist.
Yeah,
so you'll have to keep the head as it is, but then you can copy any value to the head, because that's what will identify that snake of a list.
Yeah. Right. So
you have, when you swap between 9 and 7, you want to delete 7. So when you swap this 9 to 7, then again you have to assign this 9 to 8 next, because anyway this 9 and 8, I have copy the value into the block. Okay.
Yeah, so maybe there should be one more slide after this where I swap. That is, there are two operations, right? One is swapping, and then is reassigning of the pointer. So if you start from here, you first swap. Once you swap, you no longer need this 7, but you certainly want to retain what 7 points to. So you reassign 9, which is currently pointing to 7, you make it point to 8. Okay, this is what is called plumbing, right? So instead of rerouting, the current way the pipe is going is from 7 to what 7 to 9 to 8. Instead of that, you reroute it, you plumb it, so that some kind of plumbing operation you do, so that it directly it goes to 8.
So when it directly goes to 8, automatically the link between 7 and 8 means earlier 9 and 8 will be dropped.
Between 9 and 7 will be overwritten by the link from 9 to 8. But this link from 7 to 8 will still be there, but not forever. Very soon that will disappear, because once again, since you are no longer using 7, Python will know that this is not required, and it will remove it automatically. So this is what is meant by this whole garbage collection, I think, which professor mentions, that Python will take care of that. You don't need to worry about what happens to 7. But your doubt is valid, right? So what you are asking, what will happen to the 7 which is pointing to 8? It still points to 8.
Yes.
But very soon it will get gobbled up by this Python's own memory management program, right? It will disappear. So that you don't need to worry about.
Fine.
Okay, so now the whole point is, how do we write this plumbing procedure more than one element? So if self dot
one question here.
Yeah.
Like when we create an empty list, right, with no value, no element, that time it doesn't go to garbage collection.
When you create an empty list, no. See, this is Python. How it works, something I also don't know. But when you do this reassignment, right? When you reassign 9 to 8, in some sense, you completely lose 7 track of. So from my code, there is no way I can get hold of 7 now, because I've lost my access to it.
Correct.
Right. So I think Python has some internal mechanism by which it realizes that your program cannot access 7 any longer from any part of your code. So just remove the space allocated to it. Okay, this is, I know it's a vague explanation, but I also know only this much about Python's memory
Well, if
management.
handle is not there, then it's removing something.
Exactly, yeah.
Sorry, can I ask one
where the
question?
head becomes important, right? Because if it's not a head and it doesn't have an address and a value, then obviously it is something that's meant to be deleted.
Right, yeah.
Yeah, can I ask a question?
Yeah.
Yeah, so that means to one node, you 2 pointers can be there. Like here in this figure, 7 and 9 both are pointing to 8.
Yeah, but as we just mentioned, right, the 7 will disappear, because
that's true. But is it possible? Because I mean, I thought like the way list is being constructed is that there's just one out and one in.
Correct. Yeah. So there is only one out and one in. But see, just after the plumbing operation, right, the moment you redirect this piping from 9 to 8, and after that very moment, so this will disappear. Right? Maybe so. Pictorially, I have represented it as though 7
is it that the moment the link between 9 and 8 is made, automatically the previous link is overwritten? It's no longer there.
The 7 to 8 will go away. Rather, 7, the object 7 will disappear, and along with it, the link will also disappear.
Okay.
So one node can have multiple in, right?
Yeah, that's what actually I was asking.
One node can, I mean, you could.
Means now it is 9 to 8 is linked is there.
Right.
If I want to some other node to link to 8, can I do it?
Yeah, you could write a separate function to do that, right? There is nothing stopping you from doing that. For example, not within this class, but let's say outside the class, you walk all the way down from 9 to 8, right? And then you make some other list point to 8. That is possible.
Yeah, but this is different from the list analogy which was given, that it's like a train. there's just one in and one out.
Here also, right? I mean, can you tell me which?
No, I mean, like the previous person was asking that, can you have another node and that is linked to A?
But not within the same list, not within the same. You could define a new list.
Okay. So within the same list, just one link.
Yeah, there's just one link. So in your assignment, we have a question where the links go back and forth. So that is possible, but immediately to the left of your current link and to the right of your current link. A doubly linked list, as they call it.
Okay. So this is, I mean, I'm sorry, this concept is almost similar to what we have in pointers and the values, address and the values in C++ or C.
Right, yeah.
Right?
Yeah.
But there you can backtrack also very easily. I mean, you can move forward and backtrack.
Right. I mean, here also if you add one extra node, one extra value, right? So instead of self.next, you add one more called self.previous. Then you can keep track of the immediately.
Previous value
Yeah.
also. Right. Thank you.
Yeah. So now this plumbing, right? So we were doing this plumbing. So when you identify that the first element is what you have to delete, then what you do is you do the swapping, right? So self.next, or rather the self.value and self.next have to be replaced with self.next. So let's go back to the image. I have to swap self.value with self.next.value, right? So this swap I have to do. Rather not swap, I have to overwrite sorry, what am I saying? You have to delete node 7. So one second, I kind of lost track. Yeah, sorry. I need to delete node 7. So self.value should become self.next.value, and self.next should become self.next.next. Okay, let me know if this makes sense.
And here Python automatically recognizes that self.next is an object by itself, and therefore it will refer to that, is it?
Yeah, so self.next refers to that particular object of the class node.
Okay.
Okay, so is this line of code clear?
Skipping basically, right? So like self.value, we are assigning it self.next value, and self.next, we are assigning it self.next.next, right?
Yeah,
so we are basically skipping a value.
Yeah, we are skipping that node in the list.
So first change is for the value, second change is for the address.
Yeah, exactly. Right. So first change is for value, second is for the address or the next link in the node in the list.
Sir, here self.head should mention or not?
Head. So we are at the head, right? So we are actually deleting the head, and not deleting the head, but yeah, in a sense, reassigning the head.
Yeah. Then we should again reassign the head as 9, right?
No. That is what we do, right? So this by swapping, or rather by overwriting the value of my head with whatever is there to the right, I have now deleted that particular element. Now currently my head points to the next element in the linked list.
Okay. It will take it automatically.
Yeah.
Thanks.
Okay, so this can be confusing. Please watch it again if there are any issues. Now, what happens if there are more than one elements in your list and you don't want to delete the head? Okay, this is the which scenario? This is scenario number 4, right? So you want to delete 7, but 7 is somewhere down the line. This is where recursion comes in, right? So I call delete on the next node. Since this is also not 7, I call delete on the next node. So let's write the code for that.
So before that,
Yeah.
while deleting the head or while attempting to delete that value or a sign,
Yeah.
don't we have to remove the address in the second node in order to complete that scenario? I mean, how else will that be deleted?
That is what we said, right? This garbage collection or memory management which Python has will make sure that this is gobbled up. So that will remove this 7. So as far as our linked list is concerned, 7 cannot be accessed anyway from the head. So as far as our linked list is concerned, 7 does not exist any longer.
Because there is no pointer that is pointing to 7.
Yeah, exactly. There's
And
no way
it's
of
not a head also. Okay.
It's not head also. Yeah.
Okay.
Okay. So this is the next case of scenario 4 where you call it recursively on the next. You call delete on the next node, and yeah. So we have come so far. Now here is where one very curious thing happens. So when you keep calling next delete on the next node, you will at some point hit this stage, right? Where either it is the head node or it is a singleton list. Do you agree? Like there are only these two cases possible.
Yes, sir. Other will be covered by the recursion.
Yeah. So in that case, what happens is you recursively come all this way and you try to delete the last node. And when you try to delete the last node, remember it's a singleton list, right? So for singleton list, we had this code, right? You just make it none. You just make the value none. So I'm going to go ahead and do that. So I'm going to make this none. Okay. But do you notice some problem at this stage? Have I deleted the node from my list?
No. 9 is still pointing to empty
Right.
space.
Right. So this link is still there. So I need to cut this link. Unless I cut this link, I'm not done. So whenever my recursive call comes back from this to this, I need to ask if the node I deleted, is it pointing to a null node or an empty node? Right. So I have to ask once I finish the deletion of is in my next node actually a null node? If it is, then remove this connection that I have to the next node. Right. So this is a very important step without which deletion is not complete. Okay, is this clear?
Yeah.
Okay, so let's just run this. We'll append few more.
So, but this doesn't hand the case where some node from the middle is being deleted, right?
From the middle, we'll come back to this case, right? Where you have. So let's say you want to delete. Let's say you want to delete 9. Right. Okay. So what will happen is you will recursively call and you will come to this. And now it's similar to the earlier case we saw, right? Where we are deleting the head. So
but
remember,
when we are deleting the head, we are actually swapping the next value with so in this case, like we'll be swapping 7 into 9.
Yeah.
And we'll be pointing 7 to
nothing actually. In this case, you will be pointing 7 to none.
Okay.
So it's a repeat of this particular case or previous case. Okay, we'll just execute it. 7, 10, 15, 25. I display should work. So this won't work. Sorry. So let's display it. 7, 10, 15, 25. Let's now delete. Let's try several deletes. So let's delete something at the beginning of the list and see if it works. Let me please. 1 second, I'll just delete 7. I won't display here. I'll just assume that my list is now 7, 10, 15, 25. Now if I delete, it should be 10, 15, 25. It does say that, why I didn't run this, sorry, I didn't run this cell at all. Okay, so now it has deleted, right? So 7 deletion works, 10, 15, 25. Let's now delete, say 10, something in the middle of the thing, in the middle of the list. So 7, 15, 25. Let's try 15 also. 7, 10, 25. And finally, let's delete the last element in the list. 7, 10, 15, right? So what about something which is not there? Let's say 11. 7, 10, 15, 25, nothing happens, right? So roughly that is what a linked list is all about. Right? Any questions that any of you had with respect to this?
So does this list also work? Is also immutable and global, just like your Python list? Will it work exactly like that?
Sorry, so this has none of those properties, right? Because first of all, you can't, there's no random access possible, right? So I can't say L of, there's no indexing here. So that's basically the difference between a linked list and an array. So in an array, you have what is called random access. So you can say L of 3 or L of 7. Indexing is allowed, right? Or it's possible. But
right.
Here I can't say L of, so if I write L of 3, it will throw an error. So that is one difference.
Last but one element deletion.
Yeah.
You just graphically please show how the last but one element. Means second last element deletion.
Okay, so if you want to delete, let's say, if you want to delete this one, right? 397.
397. I want to delete 9.
Yeah. So you will start with this. So this will not be. This is not a singleton list. There is something else, and this is not equal to 9. So you will recursively call delete on this.
Right.
When you call this on this element, what will happen is you will copy 7 here. So this will become 7 and 9. And then you will, this dot next, right, is nothing, none. So I will make 9.2 none. So I'll basically remove this particular connection. It will be the last, it will become the last element.
When the next dot is none, then I am pointing 9 to none. Where in the code it will addressed?
So this will be addressed here. So more than one element, this scenario, right? When the element being deleted is the head of the list.
This next dot next automatically take the value none, right?
Self dot next will be none. Yeah. So because that's the way you have designed your append, right? So if you look at append, when you appended a new node, by default, a new node has self dot next as none. You only add a particular value. You don't set anything to next.
Yeah, correct. Okay.
All right. So that is roughly what we have. Any other questions on lists?
So far, no.
Sir, I have a query.
Yeah.
So what if we delete all the elements? Then what should it return?
Okay, if you delete everything, what will happen is at some point you will be deleting a singleton list. You'll have only one element which you will delete. So sorry, I'm looking at append. Where is this? So you will set the value to be none. Okay, so let's just
So it will return an empty list.
It will return an empty list. So here, if you return, if you delete, say 25, 15, 10, and 7, and you try to display this, I don't even know. Yeah, so this true, let's remove. So true comes from this. Okay, so if you run this, you'll get none. Basically, it's an empty list.
So the node exists, but the value is none.
Yeah, it's an empty. Yeah, a node exists, but in Python, the way at least what we follow in this course is to identify an empty list. We have this convention that its value is none.
Okay.
Okay, so all right, so that is list. Any other questions on lists?
Sir, in the self.value into the program, sir, while we are assigning the, yes, so instead of singleton value, we can insert a tuple over here.
You mean here?
Yeah.
Yeah, you could add any value, any kind of value here.
So self.value is equal to a tuple. And like we do in the normal Python list, all kinds of sorting, tuple sorting, same thing is possible here.
Sorting, see, sorting on a linked list is kind of tough because any of the sorting algorithms that you have seen so far are, all of them are, they have swapping, right? Somewhere or the other, they are swapping elements, for which you need to know the index, right? You need to, so random access should be allowed, but a list doesn't have random access. Okay, so which brings me to this question. If we understand this, we'll understand what is really happening. A list in Python, right? A list in Python is actually not a list in the conventional in the technical sense of what a list is. This is actually an array. More specifically, it's what is called a dynamic array. Okay, so so do you get this, the difference between lists and arrays?
Yeah, through lecture we have some idea.
Okay, so arrays allow indexing, right? Lists also allow, lists, you can find the index of an element in a list, but that's a linear time operation. So for example, if I want to find let's take a bigger list. Do we have a bigger list? Yeah. If you want to find the index of the element 7, index is what, 0, 1, 2, 3. The only way I can do that is by traversing the list. So I start with this head, I keep going on until I hit 7. Only then I can find the index. So for example, let's maybe quickly write that function. I want to know what the index of an element is, right? So def index of self comma x, right? Assume that x is there. So assume that x,
because every node is connected to the next node. Unless I reach that node, I do not know where to go. This is the thing I need.
Exactly. Yeah.
Need that much of traverse.
Yeah. So let's say currently your index is 0, and if you hit self.value, if the current node itself is x, then you know that you can return I, right? So you are done. If not, what do you do?
I plus 1. I mean, go to the next.
Yeah. So you call this self while temp dot next is not equal to none. So while there is some other node left to go, I increment I, and I ask is if temp dot value, if I have found x here, then you just return the value of y. Okay, so I think you have to do one check for the last element. Okay, this I don't know. Let's try this out and see if it works. So instead of deleting, I'm going to print the index of, let's say, the element one at a time. Say index of 7, 10, 15, and 25. So does this work? Oh, there's some infinite loop going on. Sorry, I am not doing temp equal to temp dot next, right? So that is why I went into an infinite loop. Okay, so there is some small mistake. 0, instead of 0, 1, 2, 3 is giving me. Okay, so probably I should start at self dot next, right? Let me know if I'm making any sense or it's all total chaos.
No, sir.
Okay, so whatever it is, so if you, I hope you understood this, what we did here, or did you not follow? Is anyone there on the call?
Yes, sir.
Yes, sir.
Yeah, we got
I
it.
followed, sir.
Yeah, so if you have followed so far, then what we have essentially done is we have walked down the list to find the index of each element. So finding the index is a linear time operation.
Yeah.
Okay, so that is one major difference, and so maybe we can quickly run this demonstration of why Python lists are, so let's run this experiment quickly. Import random and time. Okay, so what am I doing here? I am creating a list of 10 power 6 elements, okay, or roughly one less than that, and I'm shuffling it. So this is a Python list of size 10 power 6. Okay. Now I am just timing this. So I'm starting the timer and I'm ending the timer. So basically I'm appending an element 0. Okay, and I'm asking how much time it takes in milliseconds. That's what this is, time in milliseconds for an append operation. I convert from seconds to milliseconds, sorry, microseconds, right? This is microseconds. So let's see the time it takes. Takes 50 microseconds, right? 15 to 10 power minus 6 seconds for appending an element at the end of a Python list. Okay, now let me, so I'll just ask you this question. Can you guess how much time it will take for inserting an element at the beginning of a list? So this is an insert operation, if you see. So append takes 50 microseconds. How many microseconds do you think insert should take?
Less than that.
Okay.
No, it will take 1 second, order of 1 second or something.
Okay, so I'll just go back to this particular list. If Python list is like a linked list, then how much time does insert take in a linked list that we see here? I mean, time meaning not in terms of big O notation.
Quick, because it's just the link that it has to resort.
Yeah, so it takes constant time, right? We didn't discuss insert here, but you just need to insert something at the beginning, right? And just make that the head. So insert is a constant time operation in a linked list, but append is a linear time operation, right? Because you have to go all the way till the end of the list. So ideally, if Python list is anything like a linked list, append should take more time than insert, right?
Yes.
Okay, let's run this and see how much time insert takes. Okay, so insert takes something like 1000 microseconds, about 2 orders of magnitude more than append. Insert takes 2 orders of magnitude more time than append. So what is the conclusion from this?
So insert is not a basic operation in Python.
Not really, right? So append and insert are in some sense basic operation. The conclusion is Python list is not a linked list.
Insert means in Python, if I insert an element, I have to shift all the element down to in array. If I insert in any position, from that position to end, I have to shift. So I have to spend that much of time by shifting that all the element
exactly
to the next.
Yeah.
That is why it is taking much time.
Yeah. So
Python, then it's an iterative operation, right? Not a basis operation.
So no, see, it's a basic method that is Python lists are equipped with, right? So append and insert are both methods. So I would say they are basic in the sense that how you implement it is not what I'm worried about, but both are basic operations on a list, Python list.
So suppose if we are using this insert in an algorithm, then while we calculate the big O, can we consider it as a basic operation then?
Okay, in that sense. Okay.
Yes.
Yeah, I get it. Okay, it is not a basic operation in that sense. It is a linear time operation. It's not a constant time operation. So sorry,
Okay,
I'm confusing this some other sentence with this. So in Python lists, insert is not a constant time operation. It's a linear time operation. So as Shomit mentioned, you have to shift the entire list by one unit every element. So it takes linear time.
Okay, sir. But append is a basic operation in Python.
In Python, append is a basic operation.
Okay, sir.
Okay, so any other questions? I'm sorry, we were not able to do any of the collected questions here. What I will do is I will pass them on to Atul, who will be taking tomorrow's session. Randomized pivot, someone asked me, that alone we can. Randomized pivot. So in randomized pivot, what we do is we don't just always take the pivot as element 0, but we randomly pick one of these elements as the pivot, right? Or we randomly pick one element, swap it with the first element, and then use that as the pivot. So that is randomized quicksort.
Okay, so we swap it with the first element.
Yeah, so if you want to
process it.
Right. So if you still want to use the same partition algorithm without changing L of 0 as the pivot, then you can swap one of these with, this 0th value and run quicksort as it is.
What is the difference between these two? Means by any advantage, disadvantage of taking randomized pivot?
See, quicksort as it is not O of n log n. If you think about it, in the worst case, it is O of n square, right? So it potentially, if you have something like a sorted list which is given to you, then you will face difficulty in getting the n log n bound. So what we generally do is we randomize the input, or at least we randomize the selection of the pivot, so that this partition of elements is more or less equal. So I get n by 2 on both sides. If not, right, I'll get 1 and n minus 1 on the two sides, right? If I choose the pivot wrongly, then this whole recursion will fail. It won't be 2t of n by 2, because a lot depends on how you partition the list.
So this 2t n by 2, the complexity calculation depends upon the choosing of pivot.
Yeah. So this is actually this is exact for merge sort. So merge sort, this is perfect. This is not the correct one for quick sort. This is only average. Only in the average case is it n log n. In the worst case, quick sort is n square. Do you see why it is n square?
Yeah, because if the given array is sorted and I have to select every time my one side is pivot is less.
Correct.
So in that way, it is the order get increased.
Right. So these are all some subtle things, but yeah, we have to keep these things in mind. Okay, so there was some question regarding this complexity, right? Week 2 GA question 8. What is that? One second. Maybe we'll quickly look at those. What are these? Week 2 GA question 5. Active assignment question. Okay, I have actually not seen this question. It seems too big. What is this? We'll go by this. Is the one who asked these questions still on the call? If yes, I will maybe take up one or two. Otherwise, I will just leave it. Okay, seems like no one who asked the question is there.
Yeah, this question, sir. Week 2 GRPA 2.
Week 2 GRPA 2. So your code is not working, is it?
No, one private case is passing.
Yeah,
but
yeah.
Other
So
is,
can you share the code?
Yes, sir.
See
Okay.
this. Yeah.
Shall I share the screen, sir?
No, just
paste it.
Yeah, just paste it in chat. I will share it in collab.
Okay, sir. Just 1 minute.
Yeah, maybe this week close, right? Because we are already like half an hour.
Sir, in Collab, we don't have all the imports.
Imports as in?
I was just trying to do import by HTML. I could not get it.
I am not sure. I don't think it is like replit in some sense because.
Okay, yeah, replit is there.
I think you have to do the pip install there if you have to import some external libraries.
Okay.
So given.
Okay, so this is. Yeah, this is a good place to demonstrate. Okay, see. I think your code there may not be anything wrong with the solution that you have given, in the sense that you may return the correct answer, but where things go wrong is in this step. Okay, so see what is, I just add that also here. Okay, maybe if I tell this, you will understand. So see, this is not a linear operation, linear time, constant time operation. This is actually linear in the length of the list.
Yeah.
Okay, so do you get that? This is, so it's, your code is not log n because of that. Okay, so
means I am failing due to time.
You're failing due to time. This is actually not a log n solution because see, let's analyze this. So this is all constant time. You're looking at the midpoint, you're looking at the middle element. So if it is greater than x, then you are calling binary search on the second half, if not on the first half, right? So technically it is, but because of the way Python lists are implemented as arrays, when you slice a list, so the time complexity of this is actually what? T of n is 2t of n by 2 plus n by 2. Right? So your is roughly, if you look at the recursion, it will be 2t of n by 2, which is so far so good. But unfortunately, you want 1 plus 1 for binary search to work. Sorry, not 2t of n by 2. This is just
Only
t of
t,
n by
sir.
2.
Yeah.
You want 1 for binary search, but what you have here is where is that? What you have here is that
This is order of n.
Yeah. So this is n by 2. If you want to be very precise.
N by
So I think if you work it out, you will get this t of n to be n. So this is linear and not logarithmic.
Got it, sir. Got it. Okay.
Right. This is a mistake I also made. So initially, I also tried solving it using the same slicing method.
But
I
sir,
thought,
very surprised because private case, you asked for this is order of log n solution, but how come my one case get passed? Then in both case, it's
that's
supposed
a
to.
smaller list probably. Same thing happened with me. I also wrote a solution where you initially slice it. First, I thought that the mistake was with recursion because you are using recursion, right? So probably because of that it is slow. But the point is not recursion here, but slicing is a very costly operation. So this thing made your code linear time and not log n time.
So what are
I'm
the
pasting
substitutes?
my code. Is that the same problem? I'm just pasting my code as well in the chat box. But I've just applied a slightly different method, but I'm also failing one test case.
Okay. This is overwrite. This is what. So here this is fine. This is fine. This is fine. This is all fine. Yeah, you are again. You're also failing because of the exact reason. Meaning being that you are slicing, so it becomes a linear time operation, and that no longer logarithmic. All right, so I think that should be it. Those we have not discussed today, please kindly we'll discuss it tomorrow. Right, tomorrow's session.
Sir, in week 3, this hashing part introduced in a very small manner. Will it be elaborate in coming week?
No, actually, hashing we have that is all we'll be covering. Hashing. Right, how dictionaries are implemented in Python using hashing. So that is mostly it.
But I try to read it from the other sources, and I find this is a very big chapter, hashing.
Yeah, true. So hashing, there's a different schemes are there, and it's a very important thing. But yeah.
In coming week, it is not covered.
No, hashing, we are done with hashing for the entire course.
And so where the application of this linked list, where we can find this application?
See, application, if you ask, linked list is some kind of a dynamic data structure, right? So you can keep growing a linked list, especially in this online settings. Online meaning when you don't know a priori how many elements you need to store. So you can just keep linking every node as it comes, right? And have a way to track all of them. But usually linked list and all is a very old data structure in the sense that it has been there for ages, right? Since the beginning of computer science, the discipline of algorithms. So typically it is found mostly in programming interviews, right? Software companies, if they interview, then they will ask you about linked lists. So at least that is where I have seen it come most often. But proper application, actually, yeah. So sorry, this one very important application I missed, which is in graphs.
Yeah, I just.
So when you use adjacency lists to represent graphs, you will use linked lists of quite frequently, right? So at least the adjacency list representation of a graph is based on a combination of arrays and linked lists. Okay, which is coming up in next week. Week 4 is all about graphs. All right, yeah, that is it then. So let's meet tomorrow.
So you will share this document, right?
This this thing I certainly share this. What is this called? Google Slides presentation.
Thank you, sir.
Okay.
Thank you, sir.
Thank you.
Good night.
Thank you.
Thanks.
Thank you, sir.
Yeah.
Thank you, sir.